All right. Hopefully folks can hear me, both here and online. Thank you, folks, for making the time bright and early in the morning to come in and for this talk. And thank you to the folks online for tuning in from whichever time zone you're in. So this talk is about bringing your data to your AI applications using object storage. And my name is Vamshidhar Kommineni. I lead product management for our blob storage service and our data management services. It's super great to be here and back in these sorts of in-person sessions. It's been great to have all these interactions with folks at the conference. So what we're going to do here is dive in to details, a little bit of background and context setting about AI workloads as we see them and storage requirements, particularly around training and fine-tuning and RAG. I'm going to presuppose some knowledge of object storage systems in general and blob storage. How many of you folks use blob storage or at least pretty familiar with it? Awesome, all of you, almost all of you. So that's great. So we won't do kind of the very basic L100 type intro stuff. We'll dive right in. And like any good build talk, about half the talk is demos and actually showing you what you can do. Everything we cover in this talk here today is ready and available for you to try. So if you're like, oh, that's interesting, I can use that, all of it is released GA material that you can go play with right away. So we have lots of content. I'm going to go a little bit fast on the slides to get you to the demos and kind of actually see what's happening. So let's dive in. So when we talk about bringing data to your AI applications, we're really talking about domain knowledge, your enterprise's data, your specific industry's public data, and bringing all of that to AI applications. Now, of course, we're all familiar with prompt engineering, but what we'll kind of zoom in on is fine-tuning and RAG, and these are the other techniques. Fine-tuning is about training your base foundation model with domain-specific data, and it's a more involved process. But it is something that folks do when they're kind of training up a model, starting with a Llama model or Microsoft's Phi models and training things up, or even OpenAI's models can be fine-tuned. And more what we see is RAG-based apps where you have data that is in a knowledge base. It's prepared in a way that these LLM apps can actually use it and gives you both inline, in-context knowledge to augment the LLM, as well as allowing you to have fresh data, because fine-tuning being involved is not something you're going to do every day or even every month. So, and kind of the differences you see on the slide here, it's about learning new skills with fine-tuning, and RAG is more like learning new facts as you go along. So object storage and storage in general, unstructured data storage, plays a pretty important part in these things. So let's start with the traditional training pipeline view, right? This is like, let's say you have a model you're trying to train from scratch, or you're one of these foundation model builders, and what do? So you start with collecting lots and lots and lots of raw data. In the case of OpenAI, it's maybe the entire corpus of human knowledge, or as much of it as they can get. And you bring that in, and you have to clean that data up. Like, that's a very common step that we all do. And then you also have to prepare that data. You're doing some form of tokenization, you're doing feature augmentation, you're doing all these things. And you're doing that, frankly, the training data preparation, what looks a lot like your traditional big data analytics pipelines. You're using Spark, you're using Databricks, you're using Microsoft Fabric, and you're preparing that data. But once you're done with that phase, you have this large amount of training data that we then feed to our GPU nodes, our GPU clusters, run training jobs, run these epochs, and take checkpoints along the way. So it's not only a read-heavy data workload, it can also be a pretty write-heavy workload because of that checkpointing phase. And all of that checkpoint data has to end up somewhere as well, sort of off the GPU cluster, if you will. And you use those checkpoints for recovery, you use it for evaluation of how good your model is. You kind of, you're in that loop for quite a bit of time. And when you're ready, you have your models, and you have to then get them out to your applications. So you have to distribute them potentially all over the world, and you're able to run then your applications and do your inferencing against those models. This is a pipeline that many of our foundation model customers run today on object storage in the cloud, including OpenAI, right? And we all benefit from having those base models. There are some industries, of course, still which use the same pipeline, train their models. We have customers, for example, automotive customers are training from scratch with the data, pretty interesting models around autonomous driving. But a lot of us have moved in this model of fine-tuning models. And that, the reason I went through the training, you can see it doesn't look that different, right? You've still got domain-specific data now, probably a smaller volume of it, go through the same sort of cleaning, prep, and creating it, but then you're using it along with the base model for your fine-tuning runs and same kind of checkpoints and looking at all of that, and then you finally end up with this fine-tuned model that you can go deploy for your applications. So perhaps the scale is different and there's a little extra steps, but the process for fine-tuning looks very similar. And when you look at that and say, hey, what are the requirements for this pipeline? What are the storage requirements for this pipeline? You have a few things. First, you've got to get the data in there. And that can be a challenge in itself, just getting large amounts of data, or even just data on your corporate network, safely, securely into Azure. We have some services like Azure Storage Mover that make it easy to do that for you. During the data preparation phase, you have to have the data available through a protocol that works well with these analytics engines. You also have to then take the trained data and be able to stream it out or download it, depending on what the training jobs are doing, to the GPU nodes. And like we mentioned, get the checkpoints back. Those are high throughput challenges in both directions. And lastly, all of this process, both collection of and cleaning of data and preparing this, as well as the checkpoints, generates a ton of data. We're talking petabytes to hundreds of petabytes, depending on the size of the model, number of parameters, size of your GPU clusters for the checkpoints, et cetera. And you really need a good way to cost efficiently retain that data, because a lot of this stuff is becoming interesting for auditability and safety and being able to kind of go back and say, what was the training data that I trained this model on? What checkpoints did I go through in the process of training? Even when you get into the inference stage, the challenges are slightly different and maybe a bit more manageable, but you do have to think about, hey, if I'm revving these models often, how do I think about model versioning? How do I distribute the model to wherever my applications, all the regions my applications are running in? How do I think about load times for these models if it's a cold start on a GPU cluster that's doing the inferencing? So you have other additional challenges that are slightly different as well. So in Azure, let's talk a little bit about what services exist, and then we're going to zoom in on one service for most of this talk. So looking a little bit more broadly, as I mentioned, preparation looks a lot like an analytics pipeline. So it works well with OneLake and Fabric. So if you have data that you're trying to kind of prepare for training, that's a good place to go. Blob storage and its data lake functionality works really well with Databricks, and it underlies Microsoft Fabric as well. If you're looking at training, historically, AI training is basically an HPC job. So there's lots of our customers who still look at having a high-performance file system, parallel file system, like Lustre. Last year, we released a managed Lustre service. Talk a little bit about that. So you might use that. Our more modern pipelines, like I showed you, unstructured data storage is just object storage, because that's the long-term place for it to land anyway for retention and cost efficiency. When you get into inferencing, you definitely have a lot more to do, especially with RAG, with structured data. So you then start to see these additional services. Cosmos DB has a lot of great functionality, Azure SQL as well. And both of them not only handle kind of storing your data for RAG, but also in some cases adding vector database functionality into the services. And blob storage, as you'll see, can be also very useful in this RAG phase. All right. So let's talk a little bit about managed Lustre. I'm really going to just have one slide on it, and then we'll go into blob storage for the rest of the talk. As the name indicates, it's a fully managed Lustre as a service. It's a PaaS service. You can choose how much throughput you need, how much storage you need, and we'll deploy it and do all the management for you. And it really allows you to bring all your applications that were running on premises, and this is as applicable for HPC as it is for AI training. We've added some little good integration, and we continue to work on that with Azure Blob in terms of bootstrapping those file systems from data in Blob, or kind of making that data cold and being able to deallocate your Lustre file system and save money. We'll continue to do more work around more dynamic HSM integration there. And it's also well integrated with Kubernetes. So if you're looking at a more modern HPC pipeline and you want to have containers instead of VMs, you can go ahead and do that too. Like I mentioned though, blob storage is really the core service that we're going to be talking about in this service, and it's the canonical service when you think about large amounts of unstructured data. The one thing I wanted you to take away and remember from what is blob storage and what's interesting or unique about it is we've spent a lot of years building what was the blob storage foundation, what we call here FNS, or the flat namespace. It has what you would expect an object storage system to have. But about 6 years ago, in 2018, we released this hierarchical namespace capability, which adds file and folder functionality, ACLs, recursive ACLs, all of the sort of file system-like capabilities. And we use that to expose additional APIs, not just the REST blob API, but a data lake API that's used by the analytics engines. It's very well integrated with Databricks today. And we have NFS, so you can just go mount your blob storage multi-protocol as an NFS file share. And we even have support for legacy protocols like SFTP for folks who are ingesting data from other legacy applications and systems and processing them with modern cloud applications. So this sort of multi-protocol single storage system really helps you avoid data silos, and that becomes pretty interesting and useful, as you'll see in some of these pipelines where you have data preparation followed by training, followed by inferencing. And you'll see that we have added to augment this additional client capabilities as well. So with that, let's dive a little bit deeper into training and fine-tuning and talk about how and what blob storage does that really ends up working well for these kinds of pipelines. The two biggest things are scale and cost effectiveness, right? We're talking about petabytes of data and terabits of throughput. And we're able to meet that. So blob storage isn't just great for cold data, long-term retention data. It's fantastic now for hot workloads, for analytics, HPC, and AI workloads. It really sings. And there's a lot of investment that's gone into that over the last few years, sort of under the covers. Blob storage has always been a cost-effective storage tier. We have multiple tiers from hot, cool, cold, to offline storage with archive tier. And you can manage your costs and do it all automatically. We have these features called blob index tags that allow you to kind of group and tag your data and then set lifecycle policies, and we'll just take care of moving data for you and even up-tiering it when you need to. We talked about multi-protocol, of course. But in terms of client work, we've done some really cool work with what we call Blob Fuse 2, which is really making it completely seamless for you to have access to object storage and your applications and frameworks as if it were running on a local mount point. So that's what we would kind of like to go off and show you. And really the key here is whether you're running in VMs, whether you're running in containers, you can take your blob storage containers, which are kind of akin to file systems or folders, and just mount them, right? And mount them and all, get near POSIX-like access from your Linux VMs or Linux containers. The code is open source. If there's something you need to tweak there, you're welcome to do that. And the core thing here is we retain the tenets of very high throughput access, ability to work with lots of scale. So let's go ahead and take a demo, look at a demo here. I have Vishnu here, and he's going to run through some of the demos. Vishnu, go ahead.
Thank you, Vamshi. Good morning, everyone. Let's dive straight into the demo. Let me switch screens. All right. So on the left, you have a D96 Azure VM on which I'm logged in. And on the right is a storage account and the container called blobfuse test. And you can see this container has 1 terabyte file, a couple of 50 GB files, and some more scripts and folders. So we're going to try and mount this folder into the VM. Now to do that, I need an empty directory. So I've created one. Let's see if it is empty. All right, that's the folder that we're going to mount. Let me go ahead and mount this folder now. Okay, that's as simple as that. Let's run that command again. And there you go. So it's as simple as that. You just mount it. You see all the files on the right, immediately on the left. It's just like working with any shared storage. And you can actually go ahead and create a file, and you'll be able to see it immediately. So that's it. It's that simple. And if I refresh it, you will be able to see the file right here. Oh my God. I'm sorry. I created in the MNT. I have to go inside the mount and then run the same thing. All right. Well, there you go. Oops. OK, there you go. So it's as simple as that. You mount that storage. You're able to work with files. Now, this is great. How performant is this? So to check for performance, we're going to try and max out the bandwidth that is available on this D96 VM, which is about 35 gigabits per second. That's across both incoming and the outgoing bandwidth. Now, before I do that, I'm going to have nload here, which is going to monitor the live network traffic. And I'm going to scale that nload in such a way that it represents 35 Gbps. Okay? So this is the live network traffic on the D96 VM. And I'm going to copy a couple of large files to see if I can max out the incoming bandwidth. So I have a couple of 50 GB files. All right, there you go. So as soon as I hit enter, you're able to see that blobfuse 2 is able to immediately pick up the files from the mount and then immediately copy it. And it is maximizing the bandwidth that is available on the VM. And if you have a larger VM, you will be able to maximize that as well. So we have made a lot of improvements that we'll talk about in blobfuse 2 that has these prefetching and caching mechanisms that enables you to max out this incoming bandwidth. Now, this is not just the incoming bandwidth, and the file just finished. We just copied 100 GB of data. And it's not just the incoming bandwidth. We can also maximize the outgoing bandwidth. So I'm going to try and write a couple of files. In the same folder, 2 of them. There you go. So the outgoing bandwidth can also be maximized using blobfuse 2. So if you're copying really large files, either in or out of blobs, then blobfuse 2 does that job really well. So we've done a lot of improvements to the blobfuse 2 to enable this process. And I'm going to quickly talk about these caching options. That's going to give you a better idea of what just happened. OK, so we've always had a file caching option in blobfuse 2 since the beginning. Like even the blobfuse v1 had a file caching mechanism. And in blobfuse 2, we introduced it with file caching mechanism. So what this does is you can choose a folder where you can bring the data from the storage account. You download the data to that folder, and then it serves to the application. So every time a file request is made, that file is downloaded to the cache and then served to the application. This is very useful when you have repeated reads, like when you're reading AI training data sets. You want to make sure that the data is available, and then you read it repeatedly. That's great. But as the data gets larger, and as you would like to read the files as and when they're coming up, like streaming, then there's obviously false shot. So that's where we introduced the block caching with streaming, and that's the demo that you saw, where we are able to use the in-memory cache effectively by downloading all the blocks of the file in parallel, prefetch them, and then serve it to the application as a stream. Now, you can configure the block size, the number of blocks that you would like to prefetch, as well as the number of parallel threads that you would like to run in this prefetch. Now, this is really useful because I have a D96 VM, and I can use 96 CPUs if I want. And if you have a smaller VM, you can always bring it down. Or if you're running another application, you don't want to stretch the CPU so much, you can always configure it. So you can use all of these options, and you can max out the bandwidth that is available on the VM that you're running in. Now, this is great. And so we know that BlobFuse 2 is easy to mount. You can access terabytes and petabytes of data directly on your VM, and you can max out the bandwidth that is available on your VM. Now, how are we going to apply this to a scenario that's more recent, which is fine-tuning and checkpointing scenario, right? So I have a small script that is going to demonstrate fine-tuning. If you see, great. Let me just show you the script first, and then we'll go through it. OK, yes, I did use ChatGPT for a bit of coding help. So I took a GPT-2 large model from Hugging Face and then downloaded it. We load that model. I use a very random text to fine-tune it, because fine-tuning is not something that I wanted to show. I wanted to show the checkpointing part. So we finished the fine-tuning. We run through 3 epochs, and then we checkpoint this file directly to the mount point that we have. So the data is going to load, fine-tune, and then checkpoint it directly to the storage account via BlobFuse. Let's do that. OK, before I do that, I'm going to go ahead and have the end load view here so you can see the live network traffic. OK, so it is loading the model. And then if you can see, it loaded in just 2.66 seconds. That's because it's already available. I'd done this before the demo. And the model is already there on my buffer cache, which BlobFuse 2 can use. It can go through the fine-tuning pretty quickly because it's a large VM. And it immediately checkpointed. And that blip that you see is what is us checkpointing 3 gigabytes of data very quickly. So yes, if you have a larger file, you will still be able to write to your storage account directly because there's no process involved. It's just in-memory cache and then directly to your storage account. All right, that's my demo for BlobFuse 2. Yeah.
This is super cool, Vishnu. And one of the things that, yeah, thank you. And the key thing is it just works. The super cool thing is BlobFuse has been out there since 2017. We've been thinking about this for a while. And it's kind of like all of a sudden, as this stuff is lit up, we're like, wait, we can use that stuff. We went and built BlobFuse 2, addressed a lot of performance issues, learned a lot about these patterns of fine-tuning and data fetch, data write, and really spent time kind of thinking about and launching the block-based caching. I think you can go use this. All of this is out there today. Just go look in GitHub for BlobFuse 2. You can go use it on your machines. So Vishnu, this is awesome. But obviously, we're all about big scale. And I want to know how you're going to show this off on a large cluster, because that's the fun part, right? It's using massive amounts of spend that we shouldn't be spending. But let's talk about how you did that.
Yeah, so I know you asked us to try and maximize whatever throughput that you could show. So yes, we were able to maximize a single VM. So we actually tried to run a large benchmark on one of the regions that we had. So we actually did an IOR benchmark. We took up a few AKS. We took up an AKS cluster with a bunch of pods, and we tried to maximize the bandwidth that was available at that moment on one single storage account container, right? So we picked a few D96 spot VMs. Of course, we don't want to disturb customers, so we chose spot VMs and saw how much we could go. We used 350 AKS pods. That's about 16,800 cores. And we mounted all of these pods to access the AKS CSI driver that uses BlobFuse 2. And we worked with around 2 petabytes of data. So what the IOR test does is it writes whatever data that you would like, and then reads it all back as fast as possible. So, and then we see how much the storage system is able to handle this load, right? Okay, so that's what we did, Vamshi, and we did manage to get some, good throughput.
Cool. So I want you to notice 17,000 cores. Our leadership hasn't figured out what the bill for this yet is. So we're hoping to have a good demo and take forgiveness later. So let's see what we were able to pull off.
Okay, so this is the snapshot from last week. Okay, so as you can see, we were able to, you can see the graph. We were able to read about 36, 37 terabytes of data in 1 minute. This is a minute, and read all back in less half the time, like 80 terabytes in a minute. But this is just the overview. But I want to actually show you the peak performance because we did this test a few times, and I want you to guess what speed we were able to achieve. Of course, this is based on the the available bandwidth at that time. But Vamshi, maybe why don't you take this, Vamshi, or even Saurabh?
I don't know, how about, hundreds of gigabits, maybe a terabit per second?
Yeah, that's the right unit. We should be talking about terabits here. So the peak throughput during this time was 8.1 terabits per second for just the ingress. And it was almost double that with the egress, 13.5 Tbps of egress. And we stopped because we don't want to disturb customer environments. And our spot VMs keep getting dropped. In fact, we were going to run it live, but spot VMs, so we don't want to risk anything else. So yes, that's how much you can push with our storage accounts and with BlobFuse too, especially mounted on AKS-CSI storage. Yeah. Thank you.
That's awesome. Thank you, Vishnu. Yeah, look at those numbers there. And this is just off the shelf. Like, we're looking at releasing this as a sample, so you can go test this yourself. You're going to run into core limits faster than we will. But you need that many cores to push the system, and it'll keep scaling. In our largest regions, this wasn't even one of our largest regions. We, again, as Vishnu said, wanted to be very cautious not to go above the sort of bandwidth at which we would really start affecting our customers. We were running this, Vishnu and a couple of our colleagues were running this overnight at like 4 a.m. or 5 a.m. to kind of stay out of the peak load on the in the US as it came online. But again, the key takeaway here, that AKS cluster was using BlobFuse, nothing else. It wasn't like some crazy fine-tuned, like really well-written code to go parallelize and download. It was just containers with persistent volumes talking through BlobFuse. All right. So what's behind this, right? Because there's got to be something interesting happening behind the scenes. And what we've done is, this work we've worked on for years now, and it's really come into its own kind of on time, and it exceeded our expectations. We call those things scaled accounts. And the idea here is we are spreading your reads and your writes across the entire region that your storage account is in. We're taking sort of these slices of each storage cluster scale unit that we have, are able to scale your account across all of them. So you're talking about thousands of front-end nodes, you're talking about hundreds of thousands of hard drives, and we're able to kind of seamlessly do that. And the best part is you, as a developer, don't have to do anything to kind of go configure this. This just works. We realize that we're throttling you, we auto-scale you, and we give you that higher throughput as you need it. And there's no real change to pricing or anything like that. Of course, you pay for transactions and all that, but this isn't something where you're like paying an arm and a leg for high performance storage. This is just your regular old blob storage pricing. So we'll switch gears a little bit and talk about RAG. And we have a lot of content here, so I'm going to go even faster as I look at the time. I think all of you know what RAG is. It's about adding domain knowledge at the time of query in line with that query. The pipeline for that looks different. Some of it looks the same. You again have domain data, a knowledge base, you clean it, you now chunk it. So you have to choose these chunk sizes because that's the context you supply to your LLM. Those chunks have to be prepared. They have to be run through an LLM. These embeddings are generated, vectors are generated, they're stored and indexed in a vector database. And then when your query comes in, that query is run through an LLM, same embedding kind of vector thing, and you run a similarity search. That's actually what vectors are, right? And when you get back the matches to that similarity search, you go get the chunks from wherever your chunk store was. You return that, you add that to the prompt, and then you feed that to the LLM and it says, oh, here's a better answer, right? So that's what's actually happening underneath the covers. And the requirements are different from training and fine-tuning. You know, of course, you still want to bring data, but it's usually enterprise data, more secure data that you know want to bring. Very new, interesting, different requirement is you want low latency access, especially to those chunks, because you are now inline in the application. Your user is waiting there. They've typed in their prompt, and you're like, well, am I going to get an answer or not? So you need to be faster. You need to be well integrated with this vector database capabilities because you don't want to be spending a bunch of time wiring all these pieces up. You also need to support freshness updates. These knowledge bases are only as useful as they are current. So as data is generated wherever industry and domain you're in, you want that capability. And last but not least, you really want great security and access control for this data, because you don't want, even inside an enterprise, what the CEO gets back as an answer with all the data is not what I should get back as an answer, with not all of the domain knowledge that I should have access to. So that all needs to be handled automatically too. So what we do with blob storage here, the multi-protocol stuff helps. For low latency access, we have this fantastic service called Premium Blob Storage that's been in GA since 2019. It's fully SSD backed, much lower latency, much better for this scenario. We have great integration with Azure AI services, as you'll see in the demo, and you can bring your own infrastructure pieces, your orchestrators, your vector databases. For freshness, we have change notifications like all the all file systems, good file systems do, but we also have this really great change feed functionality that is guaranteed, strongly consistent, in order log of changes. It's unique, and it is something that supports batch updates of your knowledge base. So if you're like kind of adding a bunch of knowledge every day or week or whatever, it's great for that without having to recrawl your entire knowledge base. And lastly, the security works really well because of how deeply Entra ID, Azure AD, is integrated. You can use RBAC, and you can have all your normal organization roles and all that. So the concept of me as a person versus my CEO is already embedded in there. And you have attribute-based access control. You can use these index tags to say, hey, Vamshi has access to project X, but not project Y. And that can be codified with tags inside the blob storage system. So enough talking, let's do demos. Saurabh, take it away.
Thank you, Vamshi. Hope everybody can hear me. So in this demo, we are going to talk about how blob storage deeply integrates with Azure AI services, right? So just to give you a sense of the setup here, this is a familiar diagram that Vamshi walked through. But what we've done is we've now put AI Search as the vector DB. OpenAI Studio is our orchestrator for retrieval and response. And obviously, all of this is powered by Azure OpenAI 3.5, GPT 3.5, and embedding models. So let's dive in. I'm just going to switch to our demo screen here. All right, so what you're looking at right now is the familiar Azure OpenAI Studio. And right from here, I can dive into Chat Playground. And before we get things started, just to make sure we don't have any kind of knowledge base, let's type in a rather innocuous and fun query. What is grit in AI? Well, gave me the English definition of grit and applied it to the context of AI. Pretty fun, but not exactly accurate. Now let's go and see how we can augment the context with our own data source. So I'm going to click under Add Your Data, add a data source. And right here in this drop-down, I can see Azure Blob Storage, right? As simple as that. I can just click through, add in my blob storage resource, which I'm going to do right here. And let's say this one. I'm going to pick a blob storage container. And as you can see here, I can now pick an Azure AI Search resource from right here. But not just that, I can also go into AI Search itself, which is where I'm right now. I can click on any search service, and I get this pretty interesting option here, import and vectorize data, which is essentially combining the chunking process that Vamshi talked about, where you need to break down your documents, but also vectorize them inline in one shot, right? So as I click on import and vectorize, I can see the option of blob storage right here, and you also see OneLake as well. So if you want to use OneLake, you can also use OneLake with what we call integrated vectorization, right? So it's very simple to set this up. Now, what I've done is I've actually added some of this context to my chat playground. The data source has been added in. This is the same query that we just looked at. Let's type this query again and see if we are able to get a more specific answer for our data source. What is grit in AI? And there you go. GRIT actually stands for Generative Representational Instruction Tuning from research work that recently happened. And how did we pull this? We actually pulled this from 3 references, which I can see right here. And if I click on one of these, it actually shows me the parameters, hopefully. And I think the references are probably, let me just pull this. There we go. So it's pulling it from this particular PDF file, which I have right here. And this is my file. And this is exactly the section where this is pulling in from. And it can actually answer some pretty detailed questions based on the chunking size that you select. So there you go. I was able to hook up blob storage with AI Search, OpenAI Studio, and essentially perform RAG.
This is awesome, Saurabh. And really amazing how well all of this stuff works together. And you can just kind of go get started right away. Again, all of this is available for you to try today. But Saurabh, you know, of course, we at Microsoft pride ourselves in providing a great platform that people can bring their own components to. So what if I want to use LangChain, and what if I want to do, use Pinecone as my vector DB? Can I do all of that with blob storage?
Oh yeah, absolutely. In fact, let's just switch to our slides here, and let's look at, we just saw the OneLake integration within AI Search, just like blob storage. So now we're going to do a demo where we are going to replace our vector DB with Pinecone and our orchestrator with LangChain. Right? This is a very popular developer framework and orchestrator. The rest of the setup remains the same. And for this time, what we'll do is we'll actually dive into a bit of a code. Right? So we're going to switch to our demo screen right here. And now what you can see is VS Code. What I've done here is to hook up a sample application that leverages the LangChain packages, the Pinecone packages. And essentially what it's doing is it is doing whatever integrated vectorization was doing behind the scenes with some code from LangChain and Pinecone. So let's go to this function here, process PDFs from blob. And here I can actually see I'm using LangChain's recursive character text splitter. And oh, by the way, I can also use the LangChain community PyPDF loader to load PDFs in and then split them into chunks. That's essentially what's happening out here. Of course, the process of generating embeddings uses OpenAI text embedding models. But the fun part is I can process and store these chunks, which is happening right here. And then I can generate embeddings from those chunks. And this is where I do the index.absurd. How many of you have used Pinecone before? OK, perfect. So this is a familiar command to you. Index.absurd is what is used to sort of upload those vectors. And then when I generate my response, I'm essentially generating embeddings from my query, getting matches from my Pinecone index, which is essentially this function here, index.query. And then against those matches, I'm retrieving the chunks from blob storage, which is happening right here, and then appending those chunks to my context. And that's actually happening right here. Retrieve chunks.append is what is chunking, is basically appending all the chunks to my prompt. And that is essentially what is sent to OpenAI models, and that is what generates the response. So let's see this in action. Let's do query what is, just for consistency, what is grit in AI. And it got matches, chunks retrieved, and it actually gave me a pretty detailed answer along with the references here as well. And that essentially is an application that works perfectly fine with the LangChain orchestrator and Pinecone behind the scenes. And all of this was done with Premium Blob Storage behind the scenes. And as you can see all the references and the chunks as the answer shows up.
And that's one of the key takeaways. It's super awesome that you can do this but you're still retrieving those chunks from blob storage. So you want that to be super performant. Now, Saurabh, we also talked about change feed as a unique feature for blob storage for batch processing. How much code is it, or how hard is it to integrate change feed into this application?
I'm glad you asked that question, Vamshi. It's super simple. How many of you have used change feed? Let me just ask that question. Okay, so let's maybe talk about how to sort of quickly enable change feed. That's very simple. You go to the data protection tab out here, and then you can enable blob change feed from right here. You can also enable change feed from code. But the code to essentially parse the change feed, which is a consistent, guaranteed, and ordered log of changes. And if you're looking at billions of files, doing this otherwise, which is to keep your knowledge base fresh, is so hard because you'll have to keep a catalog of what changed, what modified, diff the catalog, and then figure out what you need to process. But you don't need to do that with change feed. And this essentially is the piece of code that shows that. I actually get the change feed from my blob storage account, and I can actually filter the change feed based on a start time and end time. So let's say you're processing things at the end of the day, you're a finance company, there are a bunch of trades that need to be committed. You can do that very easily with change feed. And then for every event in change feed, you can just filter those events based on when a blob was created or updated or even deleted, right? And that allows you to know which indexes within your vector database do you need to update. And so based on those updated blobs, you regenerate the chunks, again using Premium Blob Storage, and then index.upsert the vectors for those chunks into Pinecone, right? So it's as simple as that, Vamshi. So it's, what, maybe less than 10 lines of code, maybe 20 lines of code, but that's pretty much it.
That's awesome, Saurabh. And it's an interesting thing that, as an aside, the reason it's buried under data protection is we built this for doing backups of Azure Blob Storage. So we ourselves needed a technology to kind of say, how do we know what changed without having all this stuff work? And then we're like, wait, this is actually kind of useful for other people too, for batch processing, not just in AI, not just in this RAG scenario, lots of places where you need to go kind of figure out what changed in your object storage system and go use it.
Absolutely. And I think one of the things which I would love to talk about is the fact that we were using premium storage behind the scenes for these RAG applications. And premium storage, as Vamshi talked about it as well, is SSD backed. And so what that does is, compared to standard storage, which is typically what most people use for transaction-heavy applications, premium delivers 3x faster RAG performance at scale. And not just that, it actually delivers 65% savings on transactions. Now, as you can imagine, for billions of files, when you break them down into chunks, you're writing those chunks, reading those chunks, it is a very chatty application because you're interacting with storage that often. And when you do that, the number of transactions blows up, right? And so you want to save that, and that's what Premium delivers. So not just that, the fact that you get speed with Premium, but you also get those savings on transactions. So that's pretty much it.
That's awesome, Saurabh. Thank you so much. And Premium Blob Storage, again, very proven quantity, has been GA since 2019. People use it a lot for interactive scenarios, which of course, this is kind of an interactive scenario when you're querying things inline, works wonderfully well, very widely available in most of the regions you're probably writing your applications in. So we're at the end of our talk, almost on time. We'll be here for Q&A afterwards, as long as you want us to be, or as long as they can, as soon as they kick us out, we'll have to leave. I want to kind of wrap up here with what we talked about in this talk. We talked about how blob storage is ideal for AI training and fine-tuning. That scale, the cost effectiveness, all of those things that you've known to grown to love are here. It's really well integrated with the analytics functionality that you need to prepare your data. And BlobFuse 2 is a fantastic addition that allows you to use it for fine-tuning with your GPU clusters as if you were working with normal mounted storage. It's also great for building RAG-based LLM apps. We've been talking about Premium Blob, you should go try it out if you haven't. It's integrated really well with Azure AI services. So if you're building these applications, you can get started in less than an hour. It's interoperable with all these other vector databases and orchestrators. And it's really easy to have freshness either in a streaming fashion with change notifications or batch fashion with change feed. And the core thing here, which we didn't get a chance to show given this length of the talk, is how well that Entra ID integration works with both RBAC and this attribute-based access control. So if you're looking at securing access and doing sort of scoped querying and scoped access to your broader knowledge base for your application, definitely look into this. It makes things a lot simpler to have that integrated versus having yet another system above that's checking access and whatnot. So that's our talk. Thank you so much for coming here and spending the time with us. And we're happy to answer any questions you have.